So let's look at how data rate and bandwidth are related. And sometimes people mix the two up in general conversation. You might hear someone say, our system doesn't have enough bandwidth, or our data processor doesn't have enough bandwidth. Are they meaning actual bandwidth in terms of frequencies, or are they talking about data rate? And let's look at the relationship. So let's take our baseband signal. We're going to consider this one here, and let's look at this waveform where we want to switch it on and switch it off very quickly to represent a digital 1 in this case. What does that, we know that in Fourier transform tells us that in the frequency domain, if I draw the magnitude of the frequency components of this waveform, then it looks like this. And this distance across here, if this is t, if you take capital T time to send it, then the distance across here, we're looking here in the passband, is the distance 2 divided by capital T. What do I mean by baseband and passband? We won't go into all the details, but the baseband is this signal. We're turning just something on and off. If we're thinking of mobile communications, for example, then we need to translate that signal up to the carrier frequency. And this is done, for example, with amplitude modulation or with binary phase shift keying by multiplying by a carrier at that carrier frequency. So I won't go into all the details here, but I'm drawing here the passband and I'm indicating what the bandwidth is that you need either side of that carrier frequency if you are to transmit this signal at that carrier frequency. And that bandwidth is 2 divided by capital T. So for example, if we had, this means a data rate. The data rate is the number of bits per second. So this equals 1 divided by capital T, in this case, bits per second, because we are sending 1 bit, it's either on or off, that's 1 bit in the time of capital T. So that's the data rate, is 1 on T bits per second. And for example, if we were sending at 10 megabits per second, for example, then this bandwidth here in the passband is 2 times 1 on T, so that would be 20 megahertz of frequency that we would need. So to send this signal, we would need 20 megahertz. Well, actually, we would need more than that. Actually, to really send this exact signal that turns on and off so fast, as these small side lobes indicate, you would need infinite frequencies if you were to really represent this sharply turning on and off. So we don't want to have infinite frequencies allocated to just our one channel, because we want other mobile phone users to be allocated to adjacent frequencies. We'd like another mobile phone user to be using this frequency band, another mobile phone user using this frequency band, all in the same cell. And if we really had this waveform turning on and off like this, they would be interfering with each other, because this one's signal would be also using frequencies that interfere with the other frequencies that are in the other bands. So we aren't able to do this. We don't want to have this interference. What else might we do? Well, let's consider if we were to try to contain all of our frequencies within a certain range and have nothing outside. What would the time domain signal look like for this frequency domain requirement of absolute band limitation? Well, it turns out to be a signal which is also a sinc. I've drawn the magnitude over here in the frequency domain. I'll draw the sinc function over here, and this is a function that would look like this in the time domain. And this is because there's a duality property of Fourier transforms. And so what we see here is that again, if we want to have a signal that's only contained strictly within a band limitation, then it looks like this in the time domain. Okay, and if this means we could be sending another signal afterwards at t later, time t later, and this signal will be going through 0, and so it's not going to be interfering with the signal that comes at time t later. This might be if we sent a 1 followed by a 1. If we followed by a 0, for example, then we would have maybe a negative 1 here if we're doing bipolar, plus and minus ones, and so we'd have a negative waveform here, and then maybe if we sent another one, another positive waveform here, and so on. And in the time domain, we could be sending all of these, and at the sample times, there's no other signals interfering. It's just the signal that we want to be sending at that time. So that would work, and our signal would be within this range. For this time of sending capital T, this bandwidth here is 1 divided by T. So for our example before, 10 megabits per second, this would be 10 megahertz, which is certainly less than infinity, and it's less than even the main lobe of this, which was 20 megahertz. So that sounds good, and they don't overlap. The problem is that these waveforms go forever. So to send this digital signal of 1 here at this time, you have to start the signal infinitely long ago. And so obviously you can't have that in practice either. So you can't have this in practice, or you don't want this in practice because of the interference, and you don't want this in practice because you have to start a long time before, and the delay would be infinite to have this exact requirement. So what do you do in practice? Well, in practice, you pick a time domain signal which looks like this but doesn't go forever. So we pick this one here, for example. This is often the one that's picked, which is time limited. And so that's going to be the signal for representing a 1. The negative of that would be the signal for representing a 0. And then it doesn't go for infinite amount of time. And then in the frequency domain, it's a signal that takes more than just this bandwidth, but it's spread out like this in the frequency domain. And we'll pick this and the amount of spreading out, and of course then you probably also put a guard band in before the next allocation for the next mobile phone. And so then in another guard band here for the next mobile phone. So this bandwidth here then is going to be bigger than 1 on T, and you might pick something like, maybe you might pick something like 20 megahertz. So this is a compromise because you're realizing you can't have it exactly finite in time, and you can't have it exactly finite in frequency. So we have a compromise. And so this is how the data rate relates to the bandwidth. Of course, I've only talked about binary here, and another thing that can happen is you could have, instead of signals that are just 2 levels, or even this is here is also going essentially between 2 levels. It's either the -1 or the +1, the way we drew it here. You could have signals with different amplitudes to represent different levels. And so, for example, maybe this was let's take this example here. Sometimes this is 0 volts and 5 volts in some systems. We could have 4 levels, for example. Let's say 0, 2, 4, and 6 volts. So we could have waveforms that look like this, but we could give, instead of just having a 0 or a 5 volts, we could have 0, 2, 4, and 6, in which case we could map them to 2 bits each. 0, 0, 0, 1, 1, 0, and 1, 1. So now, in the same bandwidth, we would now be sending 2 bits, where previously, in binary, where there's only 2 levels, you're only sending 1 bit. So this would multiply the data rate by 2. So in this case, with 2 bits, you get a 2 times increase in the data rate. So it would be 2 times 10 megabits per second in our example of 10 up here. That sounds great. Maybe you could do more. Of course, you could do more. If you had 3 bits, you would need 8 levels, and 4 bits, you'd need 16 levels, and so on. And then this would be excellent for increasing the data rate, all within the same bandwidth. And so this sounds like something you'd like to do. Of course, as always with these things, there's a penalty that you pay. And the penalty is that for the same overall power, the levels are closer together. So here they were 5 volts apart, whereas here they're only 2 volts apart. And what that means is they're more susceptible to noise at the receiver. And so the data rate goes up for the same bandwidth, but also the bit error rate goes up as well. And then further things you can do to that to compensate for the increase in bit error rate. You might send some extra bits for redundancy, for trying to check whether errors have happened. And that, of course, means you have to take up some of your data slots for redundancy bits, which then means that overall your actual data rate is reduced because you're spending some of the time sending redundant bits to try to correct for any errors that are happening. So these are parts of the trade-off. You get increase in data rate from having multiple levels, but you get a decrease because some of them come in an error. And so this is there's lots of factors, and you can see these factors that relate between the data rate and the bandwidth. And it's not as simple as simply saying that there's a one-to-one correlation, 10 megabits per second needs 10 megahertz, for example. It's much more complicated, and it's always a trade-off between the type of waveforms you choose, the guard bands that you put in place, and the amount of error correction that you're doing in your system. So don't forget to subscribe to the channel for more videos. Like the video, it helps to get others to be aware of the channel, and check out the other links for other videos.